next question. A vessel of depth h is filled with liquid of mu is equal to 1 plus y by h. Here we have the refractive index as a function of depth. Now we have to find what is the apparent depth of the vessel. Now Jay will continue with the solution.
Now see, in this question, the refractive index of the liquid is varying. So, but the properties of light does not change. So we could apply the basic properties into this and get our answer. So basically, what does happen is that every we consider an infinitesimally small uh, part of the vessel. Like, let's say this is a beaker or a vessel of a height h, that and it's filled with water, and let's consider a very infinitesimally small part, uh, which is at depth y, and, and this is the width. Let's say it's dy. Now, as the refractive index is varying, uh, integral calculus will be involved.
Okay, Jay, can you draw the diagram explaining why how integration calculus comes in? The relation between the apparent depth contributed for each element.
See, for each infinitesimally small element, there is some contribution to apparent depth, but the contribution of each element is different. So we have to sum over all the different apparent depths of the different elements. So that's why integration is involved. So we first consider an element of at a depth y and a width dy. So due to this, the diagram will be seen like something like this. Let's say there is a small part of that element uh, which is seen from outside. So the incident ray will be seen something like this. This is the normal. This and the act. Now see, due to the difference of the refractive indices, we get uh, the depth of the element different for different cases. So for each elemental length, let's say for the given for the taken length, let's say its apparent depth is a and its apparent width is dA. So in this case, the apparent depth A differs and the apparent width of the element also differs. So now since we have to find the apparent depth of the vessel, we start with the basic formula of that real depth by apparent depth is equals to the refractive index. That is equals to mu. Now Now we could extend this formula to this by applying that the real width of this small elemental length is dy and the apparent width of this small element is dA. So which is equals to mu, which is given as 1 plus the depth of the element by the depth of the vessel. So this will give, so by separating the variables we get dy by 1 plus y by h is equals to dA. Now we then integrate both of them, both the terms. For the apparent depth, since the apparent variable is zero, since for the element at the top the apparent depth is zero, so the real depth is zero, so apparent depth will also be zero. And let's say the actual apparent depth of the whole vessel be A. Now the limits of the depth will go obviously from 0 to h. After integration, you'll get y is equals to h naught 2.
Okay. So to summarize, we considered each small element in the beaker to be acting as an independent liquid contributing to the total apparent depth. Then we got a relationship between the apparent depth and the real depth for each small element. Then we integrated it over the whole liquid to get the final apparent depth. Here is the next question. In this question, a slab is placed on a prism. The prism has a refractive index of n and the slab has a refractive index of n1. We are given that n1 is less than n. Now we have to calculate I, the incident angle striking the face AB, such that the refracted ray strikes the diagonal AC at the critical angle. Now Jay will give the solution.
Now, here we see in this question, the only thing we need to know is what is the value of a critical angle for a given pair of media. And let's first consider the ray diagram for the given question. Uh,
From the question, we have the data about the prism, that is the angles of the prism, and also the refractive index. Refractive indexes at the two media where the reflection has to occur.
Now we consider the incident angle to be I and the internal refracted angle to be R1. The angle at which it's striking the diagonal AC be R2. So as we know for a given pair of media, the critical angle theta c is equals to sine inverse of the ratio of the uh, refractive indices. In this case, the critical angle is equals to sine inverse of n1 by n. So remember which refractive index which you have to keep in the numerator and which refractive index we have to keep in the denominator. So let's now from the question and from our solution we could say that R2 is equals to the critical angle. Now this angle A will be equals to R1 plus R2. From the geometry we could say that A is R1 plus R2. Since this is 90 degree since this forms a cyclic quadrilateral, so summation of this and this is 180 degree and summation of all this 3 is 180 degree. So from these two we could get that R1 plus R2 is A.
Jay, can you mark the various angles in the cyclic quadrilateral?
See, let's say this is the angle A, this is this angle O. So R1 plus R2 will be equals to 180 degree minus O. And since this and this forms a cyclic quadrilateral, so angle A plus angle O is equals to 180 degree. So from this two we get A is equals to R1 plus R2. So this implies A is equals this implies R1 is equals to 45 degree minus the critical angle, because the critical angle is R2 and the value of A is 45 degree as given in the question. Now we will proceed ahead. So Now from the Snell's law we could say n equals to sine I by sine r1. So this implies I is equals to sine inverse n by sine r1. Now so I is equals to sine inverse n sine of 45 degree minus theta critical angle. We have just plugged in the value of R1 from the thing we have calculated from here. Now by applying simply trigonometric ratio we get a trigonometric formula. We get I is equal to sine inverse n by root 2 cos theta c minus n by root 2 sine theta c. Now we get I is equals to we plug in the value of theta c as sine in as of the theta c. So sine theta, so we get as sine theta c is n1 by n, we get cos theta c as this root under 1 minus n1 square by n square, and we subtract value of 1 by n. Now from the above we get I is equals to by just multiplying n and taking into the inner bracket we get I is equals to sine inverse n by root 2 root under n square minus n1 square minus n. This is the final answer.
Let us look at the setup given in this question. The object O is placed in the refractive medium which has the shape as shown. That is, it is flat at one end and curved at the other end. The distance from the flat end is given as 20 centimeters, and the other data such as the length of the slab, such as the length of the medium and the radius of curvature of the curved end are given. Now we have to find out when viewed from the flat end. Now we are also given that when viewed from the flat end, the object O appears 12.5 centimeters deep. That is, its image from the flat end is 12.5 centimeters. Now we have to find out what the apparent depth is when viewed from the curved surface. So Jai will give the solution.
Now this question has basically has two parts. First we consider we basically divide into two parts, that is we basically divide in two cases. The first case is this, the flat part, and the second is this curved part. Note that we have not given the refractive index of them. We need to figure that one out from the information given. So in case, let's consider the case 1. When viewed from a case 1, that is when viewed from a flat surface. Now when we are considering case 1, we should forget about this part, the curved part. We need to bother about only on this part. So here we could just apply the concept of real depth and apparent depth and extend that property to here, because it just involves a flat surface and it can be just be treated as a rectangular medium from here to here.
Note again that this formula is important and recurring, and it can greatly simplify problems.
Now, so we know that real depth by apparent depth is equals to mu. So from question, the real depth is 20 centimeter and the apparent depth, that is the image of the distance of the image of the object O, is 12.5 centimeter. So we get mu as 20 by 12.5, which is equals to 1.6. So we got the refractive index of that slab. Now we go to the case 2, that is when it is viewed from the curved side. Now when we are considering case 2, we should forget about the flat side and we could just that simply consider it is as a refraction at a spherical surface whose radius of curvature is given as 12 centimeter. So this is just a formula based part and we could just directly apply a formula as everything is given in the question and we just need to find the image distance. So we could just use the formula 1 by v. We could just use the formula mu2 by v minus mu1 by u is equals to mu2 minus mu1 by r. So by taking consideration into the Cartesian sign convention, we get 1 by v minus of 1.6 by u is minus 20 is equals to 1 minus 1.6, the radius of curvature is minus 12. So from this we get the image distance v is equals to minus 33.3 centimeter. So as v is negative, we could say that the apparent depth is 33.3 centimeter from this part, from the curved surface. So the apparent depth is 33.3 centimeter from the curved surface.
So this is a very simple problem in which we use the first case given to figure out the refractive index of the medium and then directly apply refraction at spherical surface formula.